All right. So you could have eliminated x if you wanted to. I mean, maybe I should have done that before showing this method of showing the method of eliminating y. I don't know, but hopefully you still understand what I'm trying to show you. So can we eliminate x? Well, if you just dove right in and added, the x's won't vanish, right? Because if you add them, you would get 6 times x. We don't want that. We want the x's to vanish. But notice that if I multiplied the first equation by 3 and the second equation by -2, first equation by 3, right? And the second equation by -2, which is what I'm doing, then you'll have 6 times x and -6 times x. And then you can cancel. The whole point is you may have to think about it a bit, but you want to somehow manipulate the coefficients so that when you add, a variable goes away. That's the whole point. You eliminate a variable, hence the name, elimination. So here, we can multiply the first equation by 3, right? That's what I'm doing. And then you distribute, you get 6x plus 9y is 63. For the second equation, we can multiply by -2. We get -6 times x plus 8 times y is -46. You can't just multiply a coefficient by one number. You have to, keep everything algebraically equivalent. You have to follow the rules of algebra, so to say. So anyway, now the coefficients of x are 6 times x, -6 times x. Now we can add and kill off the x. That's what I'm doing down here. We have 9y, 8y, right? So when we add the 6x and the -6x, they cancel. X is gone. We get 9y plus 8y is 17y. You add these terms here, what do you get? You get 17. Okay, that's great. So we know 17 times y is 17. Okay, but can we get y? Well, yeah, you just divide by 17. We get y is 1. So we know a value of one variable. But again, we need to get the other variable. Okay? Now, how do we do that? Well, we could take this y and put it into either of these equations, either one. So once we get y, we can substitute it into either equation, and you can then figure out what x is. You solve for x. Because again, once you do that, you're back in section, I think 1.1, when we solve these kinds of linear equations in one unknown. So we have this. So we get 2x plus, so we plug it in, 1. I think we did, let me see, the first one? Yes. So we get 2x plus 3 times 1, which is 3, is 21. We're going to solve for x. Okay, I'm not sure why I wrote this twice, but that's okay. We can subtract 3 from both sides, right? And we get 2 times x is 18. From here to here, I just also moved the 2x term over, closer to the equal sign. Nothing wrong with that. So we have 2x is 18, divide by 2, we get x is 9. So just like before, we get our solution of 9, 1. So we get that answer. Okay. So that's elimination. Let's do some more examples. Are there any questions on this? Okay, let's move on then. We'll do another one. So here we have these two. We have this system, okay? Now looking at the system alone, we want to somehow be able to eliminate a variable when we add. So if I were to look at x alone first, okay, well, this is 4x, right? But this is negative 8x. Okay, well, can you add them and eliminate x? Well, not quite. But if I multiply the first equation by 2, right, 4x becomes 8x, and then you can eliminate. Okay, so let's do it. So I'm going to take the first equation, multiply by 2. Again, why did I think to do 2? Because we saw here that 4x, right, we can turn this into 8x, and if we do, we can add it to this equation, and then x goes bye-bye. Okay, so that's why I thought to use 2. So what do? I multiply the entire equation by 2. That's what I'm doing. So we have 8x, 14y, and on the right we get negative 6. Over here we have our new system. Okay, that's great. Well, let's add, although you can see what's going to happen. If we add together, we basically are going to kill off both variables. Namely, we're going to have 0 on the left, and we kill off the constants. So we get 0 on the right. So in other words, after we add, we're going to get 0 equals 0. And we saw what happens in this case. It's also right here. We get infinitely many solutions. And the equations then are dependent. So again, we have 0 equals 0. When we get something like this, an equation that's true with no variables, that tells us the equations are dependent and there's infinitely many solutions. Okay, that's great. So that's one example. That's another example, I mean. Any questions on this? Okay, so for the next one, I want everyone to give this one a shot. Not to hand in, obviously. Oh, I shouldn't say that, but, well, not to hand in. But I want everyone to take a shot at this. Try it out. Take about 5 minutes, so 4 or 5 minutes, I think. So let me stop the recording.